really fast through stuff. So, and then as always, if you have questions, you can text me, we can set up Zoom and we can talk about stuff. Alejandro, right now, I'm not planning on allowing corrections. But obviously if, I don't know if I'll post homework. I don't know if I'll have time for Nas. I'll try to do that for you guys. I'll try to get them up by Thursday, Friday. I'll try.
Also, will you post the solutions for the practice exams like last time, or just the practice?
They're already up.
Oh, okay. Because I checked and I think maybe I just saw the.
Yeah, they're in the quiz solution.
Oh, quiz solutions. Okay.
Yeah, that's where I put them. So 2A and 2B are there. I recommend that you try and do them first without them. And then, actually, I take that back. I just recommend that you don't try to memorize things because every problem's different.
Yeah, just like knowing the concept.
Right. And so there's a quiz 9 solution up. I'm going to try to get all the grading caught up this week. Tomorrow I have to lecture in my other class, which I normally don't, but I do tomorrow. And then, like I said, Thursday is going to be a quiz. It'll be pretty easy, and I don't think it'll be too tough. It'll be on torque and something like that. And we'll have a quick lab, and then we'll have a little bit of a review that day too. So anyway, to get started on today, what we're going to talk about today. Am I recording? Yeah, I'm recording.
Yeah, it says recording. Thanks, Professor.
I always forget. And by the way, there is a homework that I posted last night for chapter 12. I don't know where it went. I'm not in the assignments. So we have a homework for chapter 11 that's due on the 18th. And we have a homework, that's due on the 15th, and a homework that's due on the 16th. I'm going to change the 11 to the 16th. That is the day after our exam. Generally, I try to just make it the exam day because I don't want people to wait too long to do it, to put it off until after the exam. But there is a new assignment. On this assignment, we'll talk about it after the lecture. This assignment's actually worth 9 points because this first problem is a simulation problem. And hopefully that simulation problem will help you with what we're doing today, but we'll talk about it soon. Okay, so we've talked a lot about torque in the last couple classes. And when we had torque, we said a few things. We said that torque was equal to the moment of inertia times the angular acceleration. We also defined it as the time derivative of the angular momentum, and which was, if L is I omega, then this is just d dt, I omega, and on and on and on. We also defined it as R cross F, or RF sine of the angle between R and F in the z hat direction. But what we didn't talk about is what happens when the net torque is 0. What does that mean? If you remember, when we talk about linear acceleration and linear forces, when the acceleration is 0, we have a really special condition. And that condition means that an object's not going to speed up or slow down, that the velocity doesn't change. In torque, when we don't have a net torque, that means that the object's rotation isn't going to change. We usually mean that the object is in static equilibrium. And what that means is I'm holding my pen and it's not rotating. So my pen is in static equilibrium. And that's a really, really nice concept, because if that's true, then what we can do is we can say that the sum of the torques, which is each of the individual torques, is equal to 0. So let's say we add 2 torques, T1 plus T2, then we know those 2 torques are equal and opposite. We're going to go through a bunch of problems so you see how this works. And there's a few minor issues with them that we really need to make sure that you guys are careful about. But that's pretty much it. When an object's in static equilibrium, the torques do not rotate the object. So the object's not rotating. It's also not moving, which means that the forces are 0. We'll come back to this slide a whole bunch. But the conditions of static equilibrium, all of these have to be true. The external forces, all of the external forces have to be equal to 0. So the sum of the forces for all the external forces in X and Y and Z all have to equal 0. Also, the net torque about any axis is going to be 0. Which means if it's already rotating, it'll keep rotating. We're not going to deal with problems where something's already rotating. We're going to deal with problems where the object's not rotating at all. But the rotation, omega, the rotational velocity, does not change. So going back, you need to remember that what we're talking about is solids and their center of masses, that the center of mass of a rod or a disc is at the center, that these are uniform objects, which means that they have a uniform density, which means that the density is the total mass over the total volume is any tiny mass over any tiny volume. That is the only way we can make the static equilibrium case actually kind of work. When you see how we formulate this, those things have to be true, that we have to have uniform solids with basically centers of masses that are symmetric. Otherwise, we can't do any of the moment of inertia stuff that we've done previously. Okay, so how does this whole thing work? Let's talk about how this works. Imagine you hang a bar from the ceiling. So you have 2 wires, and I'm going to call this wire A. Let me call it B, otherwise I'm going to confuse myself. This is wire A. And there's a mass of this rod, and it has a length. So if this thing is in true equilibrium, the sum of the forces on it are equal to 0, and the sum of the torques on it are equal to 0. And we only care about the rod. So let's draw, well, let's draw the free body diagram of that. It has to have a weight, and it has a tension from wire A and a tension from wire B. The sum of the forces, which is equal to MA in the Y in this case, is equal to 0. And that's equal to tension A plus tension B minus M of the bar times G. So,
Professor?
Yes.
How do you know that up is the positive direction? Did you just?
I chose that.
Okay.
Y is positive and G is acting down.
Okay, got it.
So we only have the 3 forces. We have the tension of A, and we have the tension of B, and we have a weight. And we know that because it's not going up and it's not going down, and we're assuming it's not shaking right or left, the only forces are these. And we say that MAY is 0, and that's tension A plus tension B minus mass of the bar times G. Now, this doesn't exactly help us because we don't know what tension A and tension B are. And that's an issue. Let's say that we're told that the mass of the bar is 100 kilograms, right? But we don't know what tension A or tension B is. And while we're assuming that they're equal, they don't necessarily have to be equal. If we assume that the length of this thing is 2 meters, so it's a really long bar, right? How are we going to find tension A and tension B in this equation? We know that MBG is tension A plus tension B, but we have an equation with 2 unknowns. And so what we can do is we can find the torques, and then hopefully we can find the torques in a way that give us the tension at A and B. So let's talk about these torques. Is everybody caught up? I hope. Okay, so if we go about the center, let's try this about the center. So if we're assuming it's going to rotate about its center, and keep in mind, we know it's not rotating, but there is a tension A and a tension B. These are both located at a distance L to the half, right? Now, if you remember that torque is RF sine of the angle between R and F, the angle R here for both of them is L to the half. The angle between this and TA is 90 degrees. The angle between this and TB is 90 degrees, which is really nice. So let's find the torque due to each of these. I'm going to draw the right-hand side one first. And if I can actually remember what I'm doing, TB, this torque goes that way. For the left-hand side, we have L to the half, TA, and this one goes this way. Here comes the kind of iffy part. It doesn't matter really which way I choose alpha to be positive. We can do the right-hand rule. So let's assume the right-hand rule. So this is alpha. That makes this a positive torque. This one is a negative torque. By the right-hand rule, you're turning L to the half to TB. That is a positive torque. You're turning L to the half to TA. That's a negative. So what we write is the sum of the torques, which is 0, is L to the half TB plus, minus L to the half TA. And that says that L to the half TB is equal to L to the half TA, or TB is equal to TA.
Professor?
Yes.
Sorry, I know you've gone over this like a million times, but when you're doing the L to the half to the TA, it's negative because you assumed that alpha was positive, like turning
I'm using the right-hand rule, and
oh, okay.
When your fingers curve counterclockwise, coming out as positive, but
okay.
You didn't need to do that because obviously, had I chosen it the other way,
Z was like in the other direction, like not towards you, like against
yeah.
you.
Had I gone the other way, then TB, L half TB would have been negative, and L half TA would have been positive. But because they're equal to 0, it's the same exact equation. If I move them to the other side, So to be honest with you, yes, I should tell you, always make sure that, counterclockwise is your positive. But to be honest with you, as long as you're consistent, it's fine. Okay.
God.
So we know, going back to this, that TA and TB are equal. So let's just call them T, and we get 2T. So the tension will be MBG over 2. And we said this was 100, and let's just assume G is 10 over 2. So that would be 1,000. So this would be 500 newtons. So what have we done? Well, we used the fact that the forces are 0 because it's in static equilibrium. No, Sammy, these wires are at the edge. So going from the center of mass to the edge, that tension is creating a torque at a radius of L to the half. The lever arm of that torque caused by this tension is L to the half. Remember that, as an aside, torque, when you have some force acting at a distance r about some axis of rotation, the torque caused by this is r cross f, which is r f sine of the angle between r and f in the z hat. What you do is you place r and f tail to tail, and you rotate r to f. Now, if f for some weird reason is not 90 degrees off, let's say it's at 30 degrees here. Well, the torque is RF sine of the angle between R and F. And this angle between R and F is 60 degrees. It's actually the component of F perpendicular to R. So what we get here is we get RF sine of the angle, which is 60 in this case. Not too hard. But in our case, we're going from the center of the rod to the end. And that is half the length. Okay.
Professor?
So, yes.
Before you started the problem, you said that we would need to find torque to find the tension, but it doesn't look like we needed torque.
We couldn't assume that TA and TB were equal.
Well,
Yeah, we have no
like
reason to believe that they're equal. What's that?
Did you say the length of both of the wires was 2 meters?
No, the length of the rod. We don't
Oh, okay.
The wire length don't matter. It's the length of the rod.
Got it.
So they're a distance, those tensions are acting at a distance of L to the half, at half.
Mm-hmm.
But we really, to be honest with you, we have no way of knowing if TA and TB are equal. However, I want to show you guys something really nice. Let me make, this is, remember our first slide. This condition right here, about any axis, that means the torque about any axis of this rod had better be 0. And this actually comes up with a problem. Let's say instead we want to rotate it about here. And now we have the weight, which is occurring at a distance of L to the half. And we have tension A, which is occurring or acting at a distance of L. And we have tension B, which is occurring at a distance of 0. So about this axis, the sum of the torques is, let's draw each one. L to the half, the weight is mg of the bar. Okay, so this torque, which is, if I assume that positive, this is a positive torque. The other torque, L and tension A, is occurring, is negative, L turning to TA. And the final torque, TB, is 0 because we moved our axis. So the sum of our torques are L to the half, mass of the bar G, minus LTA, and that's 0. So TA is equal to, let me do it this way. LTA is equal to L to the half MBG the L's cancel, and we get that TA is equal to MBG divided by 2. We can similarly move our axis over to here. And now our weight is at L to the half. Tension B is at L. And so what we would get is some of the tensions on this one. I can see that this is going to be negative, this one's going to be positive. LTB minus L to the half MBG, which gives me that tension B is mass of the bar divided by 2 as well, which is cool, that we can actually put it anywhere we want to solve for whatever we want. That makes this really, really, really useful. You can always choose a point and then just find the torques about it. And the fact that you can always choose a point allows you to get rid of the torques that you don't care about. Here, I didn't know TA and TB. I can eliminate one of them by setting my axis right where that force is applied, and then I get no torque. It's simple. As long as you understand how torques work, this stuff is really nice. Where is the problem with this? Well, the problem with this comes in that you always have to have an odd number of torques. You can't have 1 and you can't have 2. Why can't you have 2? Well, imagine that all I have is the weight and I only have 1 wire, okay? If I put the axis of rotation here, I get that the sum of the torques, 0, is L to the half TA. I actually would get a negative if I choose this to be, no, I would get a positive, because I would get L to the half and TA. So this torque would be positive, and there's no way that that's 0 unless there's no tension on that rod. If there's any tension at A, that thing's going to rotate. I have to be careful that I have enough forces and torques to keep it in static equilibrium. And that sometimes is usually in these problems, it's usually a case of you have forgotten a force. You've forgotten something important. So I'm going to do something here that, let's say you forget. Let's say I have this same rod with 1 wire and it's hanging on the floor. It's actually touching the floor. So right at the center, it has MBG. Okay, so when we do the free body diagram, we do this and we say, oh, well, A is 0. We're going to choose it down just for the heck of it. Hang on a sec. Okay, so this is what I did, and this is actually wrong, right? So about this center, right, I know that I have a weight, MBG, and I have this torque that's being caused by TA. I actually have a choice as a side note here. I actually have a really nice choice. Because this is straight up, and this is my R, right? I can either take the angle of, well, let me put it like this. Let me say this. I can either find R perpendicular to T, or I can find the part of T perpendicular to R. Let me say that this is 30 degrees, so this is 60. So the torque from this, if I draw it, is either TA and R perpendicular, which would be R sine of theta. I'm sorry, R cos of theta, where theta is 30 degrees and phi is going to be 60 degrees. Or I can do, oh, and I don't want that one. I want this one. Oh God, I'm making a mess of this. Sorry, guys. I actually want, so this is 90, so this is 60, so this is 30. This is T perpendicular. Or I can do, T perpendicular and R. Either way, I'm going to get the same rotation, but this torque is either R cos theta TA, or it's R cos theta, not R cos theta, R TA, what is that, sine? Nope, cos of, why is it not sine? Oh, I know why it's not sine. Cos theta. The reason why it's not sine, you might have noticed that we say that torque is RF sine of the angle between R and F in the Z hat direction. But sine of that is equal to cos of that if these two add up to 90 degrees. So sine of 30 degrees is equal to cos of 60, and cos of 60, or cos of 30 degrees is equal to sine of 60. So this is the same as TAR sine of the angle between them. It's exactly the same thing. Either way you do it. It's a little complicated, but basically you need to find it. And we're going to do this a couple times soon. So back to what I was talking about with this rod though. So if we set our axis of rotation here, and I don't know why it does that sometimes, then the only torque that we have is this RTA. And that should tell us right away that we have forgotten something. This would be R, again, RTA, sine of the angle between R and T. That we've forgotten something, because that can't possibly be 0. So what did we forget? Well, at this point, we know we've forgotten something. And if we examine our system, we have to have a normal force here and a weight here. We always have to have at least 3 forces in equilibrium. Otherwise, you'll get a torque. If you have 2 forces or 1 force, the fact that you could move the axis somewhere and actually get rotation would mean it's not in static equilibrium. What I'm trying to get at, what I'm trying to tell you guys is make sure that if you get something that's not in static equilibrium, what it means is you've forgotten a force. So let's look at this now. So I'm going to do this whole problem. I'm going to say this is TA, this is N, this is mg, this is L to the half, this is L to the half, and I'm going to say that this thing makes an angle of 30 degrees. I know that's not 30 degrees, but I'm going to say it makes an angle of 30 degrees. Sum of the forces are equal to 0. N minus TA plus TA minus mg, right? no, the reason why it can't equal 0 is it can't be in static equilibrium and have a torque that's unbalanced. That R can't be, the tension can't be, and sine of the angle, right? So in order for it to be in static equilibrium, it has to have balanced torques and balanced forces. And if you're missing one, then you need one. We'll talk about that in a second. Okay, so that's the sum of the forces. Where do we want to put this axis? Where do we want to make it rotate? Well, it depends on what we want. Let's say we were given that M is 10 kilograms and L is 1 meter, and we don't know N or TA. So what that tells, yes, go ahead.
No, I was gonna tell you, how do you know like where to put the normal force? Because isn't the normal force because you put it at one end of the stick, but the mass of the rod is not going to be like evenly distributed because it's being held.
Lucas, what is a normal force?
Mass times gravity.
No. What is it? What is a normal force?
Oh, it's the force that an object has on a surface.
It's the force on an object due to it touching a surface. And this rod is only touching the surface at that one point. So this normal force isn't necessarily mg. No, I'll get to that, Kevin. So here, there's a normal force pushing up, and we don't know what it is. The weight here is not mg cosine. Kevin's right. We're not turning anything. We're just looking at the forces on here. There is a tension due to the wire. There's a normal force because it's touching the surface, and there's a weight. And that's it. You don't have to mess with anything at that point.
Okay.
And now we don't know the normal force and we don't know the tension. We have no idea what either one of them are. But we do know the mass, and we assume that G is 10, let's say. On an exam at this point, if you guys want to call G 10 to make it easier and not have to put it in a calculator, do it. Just tell me that you're using G as 10 meters per second squared. Okay, so if I want to find the normal force and I want to find TA, what do I do? What can I do? Well, I can actually either place the axis of rotation here or here. I can put it on either one, and it's going to give me a nice equation that I can solve with only one unknown. Let's start with putting it at the ground where the normal force is. So if I do this, and remember this is 30, this is at L to the half now, and this and is at L where TA is separated by 30 degrees. Okay, and we're putting our axis of rotation here. So I have, from the axis of rotation, at a distance L to the half, I have this force straight down, which is mg. And at a distance L, I have this force straight up, TA. And I should note that this is 30 degrees, so this is also 30 degrees. And so this is also 30 degrees, 30 degrees. Which means that this is actually, because this would be, I'm sorry, this is 30. Yeah, this is 60. Is that what you're gonna tell me?
Yes.
Yeah, okay. Yeah, I caught it. So this whole thing between them is 120 and this one's 60. Okay, so what we really need though is we need to make the torques perpendicular to each other. So what I'm gonna do is for this one, I'm going to use L to the half cosine of 30. I'm gonna use this distance here, which is this vector. I want the x component of this vector, which is L to the half cos of 30. mg, and for this one, I want L cos 30. So I want the part of L that's perpendicular to TA. That's all you have to do on these torques, because as I keep saying, one way to see this is that R cross F is RF sine of the angle between R and F, which is really RF perpendicular, or R perpendicular F, either way you want to see it. So what you need to do is find the perpendicular part of your R vector to your force. When you do that, what you see is that we have this one goes this way, this one goes this way. If I assume this thing's rotating in the normal right-hand rule counterclockwise, this one's positive, this one's negative, and what I get is sum of the torques is equal to L cos 30 times TA minus L to the half cos 30 mg. And that I can solve for the tension. I can get rid of the L cos 30 because I can cancel it from both terms, move this over. And what I get is I get TA is equal to mg to the half. All you have to do is cancel that L, cancel that. You get TA minus 1/2 mg, move the mg over. So nice, half the weight is there. Now I can do one of two things. I can go back No, Sammy. On the forces, all you do is you figure out what forces are acting on this thing. Forces and perpendicular have nothing to do with each other. The perpendicular has to do with torques. Okay, so we found that I can go over it with you again later after class, Sammy. We can go through.
Sir?
Yes.
I was wondering, when do we plug in the cosine 30 in this case?
In this case, hang on a sec.
Yeah, because the last one you just said it was mg, but this one we did cosine 30.
Right. We had to have cosine 30 because the, if you look at this, so we have a torque. So we have a torque that's due to, let's say, the tension one, right? If you draw this, you know, and you try to draw it L and TA, right? This angle between them, when you turn it, when you do this, you have to use R cross F is RF, sine of the angle between R and F. So one way to see this, knowing this is 30, then this is 30 and this is 60, right? So the angle between them is 60. So you could write LTA sine of 60, and by the right-hand rule, this is positive Z axis. So this thing's rotating positively. Or if it's easier for you, what you can do is you can say, okay, L is this way, T is this way. So what I really need is I need the perpendicular part of L to TA. That perpendicular part is cosine of 30, is L cos 30. Why do we need it here? We need it here because the force and the radius are not at 90 degrees. In that first problem where they were hanging, we didn't need it because it already, naturally, the torques were at 90 degrees. So here, if this is L to the half and this is L to the half, we didn't need the cosine because L to the half and the tension are 90 degrees off each other. We could write it this way, as this torque is L to the half TB sine of 90 degrees, but sine of 90 degrees is 1. Does that make sense, Kevin?
Yeah, thank you.
Yeah, cool. Okay, So after all this, what did we find? Where are we? We found that TA was mg over 2. So we could plug this in and put mg to the half, and we would get 0 is n plus mg to the half minus mg, or so this is 0 is equal to n minus mg to the half, or n is equal to, moving that over, mg to the half, TA is equal to mg to the half. Now, you might be thinking, wow, so the normal force and the tension evenly divide the weight. Yes, in this case, but only because they are each at the same distance away from the center of mass. If for some weird reason, let's say the wire was hanging, at, I don't know, L to the 4th away from the center, and the normal force was here, these would not be equal. You would have to figure out, well, I take that back. No, they wouldn't be equal. Anyway, the main point of all this is that when we do this, you sum the forces and they must equal 0. You sum the torques and they equal 0 about all axes through the object. Otherwise, it's rotating. So you might need to use that a couple times, use a different axis a couple times to get rid of particular forces that you don't know. It can get quite tedious. In fact, it gets really tedious. The other hard thing is that if you're not good at understanding forces, then things start to get tough. Let me ask you this. This is kind of a check your understanding. And I think this was kind of what Lucas was trying to get to. If this thing's sitting on the ground, how do we know that there's not like a friction force keeping it from sliding to the right? I'm sorry, sliding to the left. How do we know? Well, if we do the sum of the forces in the X, we get force of static friction. And if we do the sum of the forces in the Y, we get 0 is equal to N minus T minus mg plus T. And this has to be equal to 0. Therefore, okay, maybe it's there, but it's 0, or it's not there, whichever way you want to see it. The condition is it cannot be moving. It cannot be accelerating in any direction. Therefore, you know that either the static friction force is 0 or there's no static friction force, whichever way you want to see it. I don't care which way you see it. That's not always the case. In fact, there's some really tough problems where you do have to deal with it. And we're going to talk about those in a second. But what about additional masses? So we're going back to the whole thing here. Okay, let's say this whole thing is 8 meters long, and right at, starting from here, this is X is equal to 0, so this is X is equal to 8 meters. At X is equal to 2 meters, I have M1. So again, tension B, tension A. Now I have this M1 and I still have my bar. And the center of mass of the bar is at 4 meters. So sum of the forces are TA plus TB minus M of the bar G minus M1G. So notice there's no radial vectors here. There's no vectors at all here. Well, they're all vectors, but there's no radius vectors here. And this has to equal 0. So now, can tension A and tension B be equal? And the answer is no, because now I have this weird mass off to one side. That comes in, as we just said, if I draw I should note that I'm only concerned with the bar So the bar has,
Buster, could you go back for a second, please?
yeah. What all I was going to do was just do a quick M of the bar, M1G, TA, just draw it like a free body diagram, which you don't really have to do. A is 0. It's not moving. There are no forces in the X direction. Notice that too. We're going to talk about signs at some point, but there's no forces in the X direction. So I'm going to skip the next slide and go to torques. Okay. Now, if we say that the mass of the bar is 100 kilograms and its length is 8 and the mass of 1 is 2 kilograms, we don't know TA and we don't know TB. So now we have to find TA and TB. Where do we want to put our axis of rotation? Just to make it easy, let's put it at TA. So we're going to put it here. And we're going to assume it's going to rotate in the normal counterclockwise positive alpha. This is where M1G, remember, we said this one was at 2, this was at 4, this was at 8. Tension B, right? We have mass of the bar G, and I usually write L, sorry, I'm going to write 2 meters, I'm going to write 4 meters, and then finally at 8 meters, and you kind of run out of room. But I draw them like this because I don't need to do the torque diagrams.
Was it on the 2 and the M1 on 4?
What's that?
Bar on the 2 meters and the M1 on 4.
I'm sorry, I can't hear you pronounce.
The bar was, I think it was on 2 meters from the T alpha.
Yeah, this was at 2.
Yeah.
This is at 4, and the tension is at 8.
Yes, but I think you flip it.
What did I do?
The bar is 2 meters from.
No. The center of mass of we're going around this end here, Pranav.
Okay.
So this mass 1 block is at 2 meters away. And the center of mass of the bar is at 4 because it's 8 long, half of that. And then the tension B is at the full length. Does that make sense? Or am I confused?
Go to the second slide, please.
This one?
Yes.
Okay, so this is our axis of rotation, and we're putting it around the left side.
Okay.
So that block is 2 away. M1
The block is 2 away, but you put M1 in 2 away.
Yeah, that's M1.
Oh, you put block as M1?
Yeah, this is our M1.
Oh, okay.
Yeah, the bar is the center of mass of the whole thing, is at 4, which is the center point. And then the tension's at 8. So this is M1, the little block. This is the mass of the bar times G. And then the final one is actually going the opposite way, TB, and that's at 8. So when you do this, you can see that this one is positive, this one is negative, and this one is negative, right? So our sum of our torques is 0 is, it would be 8 times TB minus 2 times M1G minus 4 times M of the bar G. Okay, so doing all that, solving this for TB, if I move it over, I would get TB is 2 times M1G minus or plus 4 M bar G over 8. And that I can plug numbers in. What did I, oh, M1 is 2. So this would be 2 times 2 kilograms times 10. So 40 plus 4 times 100, 400 times 10 is 4,000. So TB would be 40 plus 4,000 divided by 8, which is 40 is 505. So tension B is 505 newtons. What about tension A? So if I want to go back and find tension A now.
Professor?
Yes.
So in your free body diagram they did on the previous slide, is that only solving for tension B?
This free body diagram here, or this?
No, the other one. Because I noticed you didn't put tension A in it. I was wondering
Here.
if you're only solving for tension B in this case.
You mean on these torques right here, Kevin?
Yeah, to the left.
I got rid of tension A by putting the axis of rotation at tension A.
Okay, got it.
There
Thank
could
you.
be no torque there because there's no radial, there's no R for tension A when we put it here. So now we can turn around and do the same thing at tension B. However, for tension B, when we do this, now let's look at a few things. For 2m of the bar G, we're now at 6 to the tension of M1G, and we're at 8 to tension A, and that should be straight up. So the sum of our tensions about this one, this is going to be positive. If you can't see that, 4 and MBG, this is rotating positive if we assume that this is positive. And 6 and M1G, again, positive. And then finally, 8 tension A is negative, other way, by right-hand rule. So this becomes 4 mass bar G plus 6 M1G minus 8 TA is equal to 0. And TA is equal to 4 MBG plus 6 M1G with a minus sign divided by minus 8. So that goes away. This is 4 times 100 times 10 plus 6 times what? 2 times 10? So I get 4,000 plus 120, so 4,120 divided by 8. What would that be? 515. So TA is 515 newtons. So you can see that in this one, TB was 505 newtons and TA was 515. So looking back at this picture, this is 505 newtons, this is 515 newtons. This mass was 20 or 2 times G, so this is about 20 newtons, and this mass is 100 times 10, so 1,000 newtons, right? So you have a tension of 515 and a tension of 505, and they have to add up to these two forces. This was 515, this is 505, this is 100 times 10, and this is 2 times 10, this is 1,000, and this is 20. So minus, this is 1,020 minus 1,020. Now, when you solve for TA or TB, all you really had to do was go and plug that back in. I could have plugged in 505 and solved this for TA. I didn't have to do the torques twice. But I could if I want. That's the really nice thing about static equilibrium is everything's zero. As I said, the only hard thing is what if you forget a force? And if you forget a force, usually the fastest way to figure out if you forgot a force is you'll see that the sum of the torques about some axis is 0. And it can't possibly be 0. Like, let's say you forgot tension B and you tried to do it around there. And so you got that the sum of the torques was 0, but it was equal to 2 M1G plus 4 MBG. And you're like, wait, that's not true. That can't possibly be 0. So you know you've forgotten something.
Professor,
Yeah.
can you go back to tension A? Why was it negative? Is it because we're in the negative X now?
It's not negative. Where was it negative?
No, tension A, that looks like a -8 in the bottom.
Where?
Where you stop for tension A.
Here?
Yeah.
Oh, no. So what I got here is when I'm going around this, the right-hand side, these two torques are going to be positive if I choose alpha to be positive counterclockwise. That being the case, then TA is going to be negative. What that really means is these two are going to try to rotate it, cause it to rotate to the left, and tension A is going to try to cause it to rotate the other way, back to the right.
So that just means that if one's positive, the other one has to be negative.
Right, in order for it to balance. And this equation, I could have moved over and got a positive. I just left it. A torque by itself, Sammy, will never equal 0. If you have a force that has some value, then you have a torque, as long as the force is acting at some radius. What were you saying?
So, but like when we're like computationally, it doesn't matter, right? We can just put it
I'm sorry for coughing so loud in all your ears.
No, it's okay.
Yeah, computationally, if I move this equation right here to the other side of the 0 or the other side of the equal sign, it all flips signs, which is as it should. That's pretty much why, even though I'm using the traditional right-hand rule for alpha in this case, it really doesn't matter. You just need to make sure that whatever way you choose to be positive for alpha, you keep your torques consistent with that. So since I chose it to be positive and these two torques here, the torques due to these two weights are both also in the same direction that I chose as positive alpha, they get a positive. TA becomes negative because I chose by the right-hand rule for counterclockwise. And TA is trying to make it rotate clockwise, which is kind of cool. But then doing the math, I didn't bother to move it over. I just left it on its side. I don't know what these dumb dogs are doing. Okay, we've done that. I want to do the ladder problem because the ladder problem is kind of the same thing. Really, honestly, you guys, there's two different problems. There's the tension with wires and the bar is horizontal, and there's what we call the ladder problem. And the ladder problem is if you put a ladder against a wall and you have some static friction, right? How high can you climb on that ladder before it slides? That is the ladder problem.
That's horrible.
It's not too bad if that was meant for me, if it wasn't off. So now, problem number one for you in this, you're going to stand here. Okay, so you're going to stand somewhere and you want to know how high you can go before that wall, that ladder slides down the wall. So what we have to do is figure out the forces on this. If we assume the ladder is, I don't know, 4 meters long, your mass, I'm going to assume is 60 kilograms. The ladder's mass is only 40 kilograms. And static friction coefficient of the ladder against the wall or the ground, I should say that there is no friction on this surface, but this surface has friction, static friction with mu s, and mu s will be 0.2. Okay, so our first challenge here is the forces. We've got to think carefully about the forces because we have forces in the y and x. So let me draw this in a little bit different, better way. And then I can clear this up. All right, So forces that we know right away. Oh, I should also say that you are at, you are 2/3 of the way up. So this is 2/3 of L, which is 8/3 meters, is how far you are up that ladder. So at 8/3 L, your weight at the halfway point at L to the half is the weight of the ladder. What about the other forces though? Those are easy. Down here, we're going to have a normal force, which I'm going to call normal force in the Y. Here, normal force in the X. So normal on all surfaces. That's important. Make sure you have a normal force on all surfaces. Make sure that you get weight for all masses. And our weights are mg. Now, I know that I have friction down here. And I'm going to assume it's keeping the ladder from sliding to the left, the bottom of the ladder, from sliding to the left. So I have this force of static friction, F of S, which I'm going to assume is mu n y. Mu n y, right? It's the normal force down at the bottom of this ladder. And that normal force is not just these two masses. That normal force may have more than just that. We'll see. But anyway, okay, so we have those forces. I think that's good. We don't have friction on this wall, so there's no up or down because there's no friction on this wall. There's no force up or down at that point. I think we accounted for everything. So what do we get? We get the forces in the X and the forces in the Y are equal to 0, assuming the ladder isn't moving. What are the forces in the X? Well, I have the force of static friction and I have the normal along Y. So that means that the normal along Y has to be the force of static friction. In the Y, I have the normal in the, sorry, this is normal in the X. Normal in the X, I should have called it that. Normal in the Y minus ml, the mass of the ladder, minus your mass. So ny is equal to mlg plus myg, and nx is equal to force of static friction, which is mu ny. And at this point, I don't actually have to do anything with torques at all, which is really nice. I can actually solve this so that I can find what nx and ny are. Because, as I said, what did I say? Your mass was 60 and mass of the ladder was 40. So 40 times 10 plus 60 times 10, which is 1,000 newtons. And if I plug that in at 0.2 times 1,000, that is what? 20% of 1,000 is 200. And I'm done, which isn't too bad. But now, what if I didn't know, trying to think, what do they usually not tell you? And I don't remember. We'll get to that in a minute. But let's talk about these torques. Normally, am I forgetting something? Because normally you find nx, that gives you ny. Yeah, let's say we don't know your mass. If we didn't know your mass, and we're going to do a lot of problem homework, but let's say we didn't know your mass. And we know that this thing is just on the verge of slipping, as in the previous case. So we have nx, we have Fs, we have Ny, we have your mass times G, we have mass of the ladder times G, and R for you was 2/3 of L, R for the ladder was 1/2 L, and R for Nx is full L. Okay, so that means that this is at L, this is at 2/3 L/2, and this one's all the way up is at L. So now what we would need to do is we want to know what Nx is. Okay, so we can put our axis of rotation at the bottom. I'm going to draw this in a kind of weird way. So Nx is at the full L, which I think I said was 4, right? Your mass is at 2/3 L. So R is L. R is 2/3 L, which was 8/3 M. And mass of the ladder was at L², which is 4. Okay, so about this axis of rotation, not knowing what our angle is, let's find each of these torques. So first torque, MLG. We know that R is this, but we need that R is L², but we need R perpendicular. We know this angle is, well, we don't know what this angle is. So we know that this is R cos theta, right? And then this torque, if we assume that this rotation is positive, this torque will be negative, and this torque will be M ladder G R cos theta. We don't know what theta is yet. All right, so what about yours? Well, same thing for your weight, except that our R is now 2/3 L. So R perpendicular is, and I'm going to change this to L² because this is L² cos theta. So this R perpendicular is now R cos theta. Now this R, so let's call it R prime, which is 2/3 L cos theta. So this torque is M of U G 2/3 cos theta. All right, and then our final one is the more difficult one. R is equal to L and N of X. So we need R perpendicular, and this, right, if this is theta, we need L sine theta, which is what this R perpendicular. So this torque is L sine theta, and X rotating positive. So this torque is NX L sine theta. And now sum of the torques is equal to 0. These two are negative. The two are both negative. This one is a positive torque. So I get NXL sine theta minus M of the ladder G L² cos theta minus MYG 2/3 L cos theta. So my problem here is that I have sines and coses. I don't know what the angle is in this case. If I put this on a better axis so you can see it more clearly. So I have the sum of the torques around the bottom axis is NX times L. times times sine of whatever angle the ladder's at. So this thing's at L and X points down. Minus your mass times 2/3 L cos theta. And so that is at 2/3 L. I have your mg, your weight. So this one's trying to turn it counterclockwise. This torque's trying to turn it clockwise. M ladder G is at L to the half. And so this one, L to the half, M of the ladder. So those two are trying to turn it clockwise. The normal force at the wall is trying to turn it counterclockwise. So what do I do? And this is equal to 0. So what do I do? Let's set it this way. MYG 2/3 L cos plus MLG L to the half cos. Now, if I divide through by sine, X and L, I get MYG times 2/3 1 over tan plus M of the ladder G 1/2 1 over tan. All I did was I divided through by sine theta and L. So divide through by L sine theta, L sine theta. Sine over cosine is tangent. So now I don't know what the angle is, but I can find it if I go back to my previous, where NX. So since I have that NX is equal to MYG times 2/3 plus MLG times 1/2, all times 1 over tan that, NY was equal to mu and X, I'm sorry, nope. What was it? NX was also equal to mu NY, and NY was equal to mass of the ladder times G plus your mass times G. So I would plug it in here. If I plugged in mu MLG plus MYG, as I said before, this is 0.2, this was 1,000. So this is 200 newtons. And if I wanted to solve for tangent, multiply through by tan, divide through by NX. And so I get that tan phi is MYG times 2/3 plus MLG times 1/2 divided by 200 newtons. This side is, MY was what? What did I say? 60 and 40. So this is 60 times 10 times 2/3, that's 600, 1200, 400. 400 plus this was 40 times 10 times 1/2, that's 400. 200, so 200. 600 divided by that is 300. And phi is therefore equal to arctan of 300. Do I want to do that? That seems a little big. Sorry, 3. I'm done. This is 600 divided by 200. This is 3. Hang on one sec. which is 71 meters or 71 degrees, 71.6 degrees. So let me, yeah.
Could you tell me where the tan phi came from?
Okay, so let's go back and talk about this whole thing and I'll get to it.
Sorry, I'm sorry.
So the forces in the X and the forces in the Y are 0.
Okay.
This is, if we go back and look, this was static friction force minus N of X. Static friction force is mu Ny minus Nx. Then this was Ny minus Ml minus Myg. And then the sum of the, hang on a sec. So the sum of the torques about that bottom axis, about here, we don't have to worry about Ny or Fs because they're on the axis of rotation. But the other two torques, or the other three torques, would be, if we look at these, so we would have for, actually let's go here. For Nx, it's at L, but we want the part of L perpendicular to Nx, which is, if this is theta, right, then we want L sine theta. So first torque is NXL sine theta. Then we get, for the other two, this one we want the part that's perpendicular. So this is 2/3 L cos theta. Same with this one, this is L to the half cos theta. So what we get is we get M of the latter G, which was 1/2 L cos theta. And the final torque is your weight, which was at 2/3 L cos theta. Now, since this is equal to 0, Lucas, you can divide through by sine, or we could move this over, and what we get is NXL sine theta is equal to MLG 1/2 L cos theta plus MYG 2/3 L cos theta. So divide through by sine on both sides. And cos over sine is 1 over tangent.
Yeah, but in the next one, you didn't write, in the next slide, you didn't write 1 over tangent.
Yeah, hang on a sec. NX, so the L's all cancel as well. And I forgot to put it here. On the next slide, you mean on this one?
Yeah, you wrote tangent, not 1 over tangent.
Oh, because it was 1 over tangent, but then I moved it to the other side. So,
okay. Got it.
Where did I say? Oh, yeah. So this is, 1 over tan. But then if I multiply through by tangent, so what I get actually is this. I get tangent of theta is over NX over NX. That ends up being my equation. So I can find theta. Now, what's interesting?
Phi.
What's that? Sorry, Farnaz. What did you say? Farnaz?
What it comes at the end, phi instead of
I could call it phi if you want. I don't. It doesn't.
Oh, it's not as it's not 90° minus theta. It's its own theta.
Yeah, no. This is actually the theta from the ground.
Yeah, I thought that you changed it to phi.
No, I didn't.
Okay,
I didn't.
thank
I
you.
wanted it to be. I want it to be the angle from the ground. The reason why is, what does this angle mean? So when I do this with the ladder weighing 40 and U weighing 60 and gravity being 10 and NX being 200 newtons, what happens is I get that theta is 71.6 degrees. What does that mean? That means that that's the maximum angle you could have it at where static friction would keep the ladder from sliding. If you went any further up the ladder, it would cause it to slide. Or if you tried to drop this angle, it would slide, which is a little weird. So let's see if we can figure out what would happen if we increase this angle. I'm gonna try and figure out a way to show. So we got in this one that 0 was equal to, and I wrote theta, 0 was equal to nx L sine theta minus myg. You were at 2/3 L cos theta minus mlg L to the half cos theta. So if you increased your torque, it would cause, so if you actually went higher, it's going to cause this thing to rotate. It's going to cause it to slide backwards. And we're assuming that nx is equal to mu ny, which if nx increases, then it's also going to I'm sorry, if nx decreases, it will slide. Trying to find a way to say this that actually makes sense. We'll look at it when we do the ladder problem. I think it'll make more sense there. So the other half of this chapter, actually the third section, is something called elasticity. And you actually probably all have seen this in chemistry or somewhere before, or high school physics. Elasticity is one of three things. It's a lot more useful for engineering, but we see it in physics, and you see it a little bit in chemistry and biology. But basically, imagine I had a wire that had a certain length, and I pull on it with a force. And after I pulled on it with that force, there's an increase in the length of the wire. So L prime is now L plus delta L. What elasticity helps us figure out is what that change is for a material. Believe it or not, even like a metal wire, if you hook it up to something that's strong enough or try to hang enough weight from it, the metal will actually stretch, much like cloth will. The next type is what's called deflection or shear. So how many of you have probably taken a pencil and held it like this until it snapped, like you bend it and it snaps? Basically, the bending of a rod is the deflection. So if this point was here and now it's been moved to there, deflection is something called delta X. And shear is that deflection. The final thing is what's called hydraulic compression or stress. So imagine if you applied a pressure evenly to the outside of a sphere and it shrank. It actually compressed its volume. So this is a volume change. Those three things have basically the same formula. If we're trying to find the change in volume or the deflection or the change in length due to forces, we get this really nice equation, which I'll get to in a minute. The problem is this is all experimental stuff. And so you'll be given something called Young's modulus for material. Some books will tell you that Young's modulus is one thing, and then they'll call like the shear or deflection strength beta. There's different letters. I'm going to use the letters associated with different coefficients from our book. I don't like the letters our book uses, but I'm going to use them. So the first thing you have to know is if we go and look in our book, I want to show you this. So if you go to your textbook to chapter 12, and you go to section 12.3, elasticity, if it will ever open. Maybe. Okay, so imagine that, I don't want to do that, don't do that, don't do that, don't do that. Okay, so these are examples of basically linear stress here, where there's a force that pulls on either end of it and causes it to stretch by delta L. There's deflection, where the change is delta X. That is a shear force. It's a force that's perpendicular to the cross-sectional area, which we'll talk about what that is in a second. And then there's this volume compression due to pressure or force applied at all sides. Now, what you have to know is the equation that I'm going to give you, if we measure what's called the strain over the stress, this is only relevant in a very small linear region, okay? So we have an equation that says the force over the area is equal to this constant times delta L over L, okay? So they've gone here and they've basically are trying to find Young's modulus. How are they doing that? Well, they're dividing F divided by A, and I'll talk about what these are in a minute, by the fractional change gives you Young's modulus. And whenever we see something like this, we know that that means graph Y versus X. Whatever your constant is on your graph, that gives you the coefficient of whatever you're searching for. In this case, we're looking for Young's modulus, where the stress is force over cross-sectional area, and the fractional length change is our denominator. So when they do that, when you do this, so as you start pulling on like a wire, right, with some constant force, only in the very early region is there this nice linear elastic range. And so you need to know that this only applies in that first small linear range. At that point, what happens? It starts to come apart. And you actually see this weird moment where Young's modulus actually drops momentarily. And then Young's modulus increases at a different rate until it ruptures, and then you're done. Which means, so if you imagine this thing like taffy, there's this weird break point, or there's this weird plateau point where it momentarily gives up, and then it starts fighting back again until it breaks. Really weird stuff. But we're only concerned with this small little linear range here. So we're only concerned with very small changes of L versus the length. So we're talking like a meter long wire that's changing by a micron, right? Very, very small changes in L versus length, or very small deflections versus length. Very small volume changes. Okay, so as I've said, the equation that you need to remember for each of these is exactly the same. It's force over cross-sectional area is length change over length. This is the fractional length change. This is for stress. Young's module is this weird curvy Y that they call it. Trying to find it, they have it here for you. They don't even really write it that way. So shear, hydraulic. Oh, they write it as E. So in most books I'm used to, they write it as a Y for Young. But our book writes it as E. So if you see E, that is the linear or the fractional length change lengthwise of an object. For a deflection, a shear, they use this G, and it's really simple. It's just delta X. Same force over area is G delta X over L. So this is for shear or deflection. And then the last one is F over A is equal to beta delta V over V. Okay. So that's not too hard. That's our final thing. You might notice something. This now has a little P instead of F over A. Okay, we're going to talk about what that is. You should know what that is, but we're going to talk about what it is. So when I have a wire, and
Can you go back real quick, please?
To this?
Yes, please. Thank you.
They're almost exactly the same except for the delta L over L. So they just use a different letter for stress, and they use a G for deflection, and they use a beta for compression.
I got it. Thank you.
Cool. Okay, so for a wire, we're assuming that the force is being applied equally along this area. So this whole area. So the cross-sectional area, which we usually write like this, would be the area of this disk, or pi r squared, whatever this radius happens to be. For a square, let's say you're pulling on one face, you're applying pressure to one face. You could be pushing in on it, whatever. So so A here is length over width. For a sphere, right? Well, if you imagine this sphere cutting through, the cross-sectional area of a sphere is what? It's either one of two things. It's either the surface area for compression, what is the area of a sphere? 2 pi, am I losing my mind? Surface area of a sphere? I know someone knows it. I'm having one of those senior moments, sorry. Area, sphere. Yeah, 4 pi. I'm like, why is that? So 4 pi r squared, or if it's moving through something, it looks like a circle. So it depends, but for volume of a sphere, it'll be 4 pi r squared. Just remember that. We're going to do a few examples of this. So imagine, and the last thing I'm going to say is pressure, which we're going to get to when we do fluids. Pressure is force over cross-sectional area, okay? So if you push on something with your finger, the pressure your finger exerts is the amount of force averaged over the surface area that you're pushing on. Wind pressure blowing on you is equal to surface area, force over surface area. So let's say that we stretch a thin steel wire. We're going to see how this works. We want to know what is delta L if we apply a force of 600 newtons to a wire with a radius of 0.01 meters squared. So the cross-sectional area of this wire is 0.01 meters squared. And we're applying a force of 600 newtons, and we're trying to pull on it. So we're pulling up with a force of 600 newtons, and we're assuming that this end is anchored, and we want to know what the delta L would be. So F over A is E in your book, delta L over L, multiply through by L, divide through by E. Delta L is F A L over E. Our force was 600. Our cross-sectional area is 0.01. Our length, let's say our length is a 2-meter long wire. So 2, and then what is E? How do we find E? Well, you can either look it up, or for our book, go to, if you're doing like a Wiley problem and you need it, go to this table that is given, table 12.1. The density, Young's modulus E, it gives ultimate strength and yield strength. We only need this. But notice that is 10 to the 9th newtons per meter squared. 10 to the 9th. 200 times 10 to the 9th is 2 times 10 to the 11th. So E for steel is 2 times 10 to the 11th newtons per meter squared. 2 times 10 to the 11th. Now units, newtons, meters, meters squared, newtons over meters squared. That means this cancels, this cancels, this cancels, this cancels, and we get meters, which is great. So what is this fractional change going to be? 600 times 2 divided by 0.01 divided by 2 times 10 to the 11th is 6 times 10 to the minus 7 meters. Now, 6 times 10 to the minus 7th meters, a micron is 1 times 10 to the minus 7. So this is 0.6 micrometers. That is insanely small. A cell in your body, a blood cell, is usually like a micron. That means that a 600 Newton force on a 2-meter long wire with a cross-sectional area of 0.01 meters squared, which is a centimeter. Well, it's 0.01 meters squared. That would only change it by half of a micrometer, which is so small. You would need a pretty good microscope to be able to tell. Steel has a very big Young's modulus. You can see that, like, one of the problems here is as we look, these are all in 10 to the 9th. Aluminum is a lot more pliable than steel. Glass has almost none. But you might be asking yourself, why is there this little B that says compression? Okay, here's the big problem with elasticity and why elasticity is kind of not, I don't know. Our book doesn't talk a lot about this, and it really should. So when we're talking about the fractional length change using Young's modulus, we're assuming that you're pulling on it. So this is stretching. Now, here's the funny thing, okay? Some objects, if you push down on them, so the pressure on this is force over area, and if you assume that this is like a stone made of concrete, it would be the area of that surface. Concrete has a really, 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 really high E. Really, really high when you step on it. It's got really good compression strength. However, unfortunately for concrete, if you pull on it, okay, E is a lot lower. I don't know the exact numbers, but concrete, when you pull it apart, breaks apart really easily. But it's got really good compression strength. They don't really mention that. They mention it a little bit about whatever it was, bone, was it? that bone only has good compression strength, concrete as well. All of these E's are experimental numbers that someone in a laboratory, pulled something apart until it broke, and they did it over and over again, and they got numbers. You can actually go online and look up Young's modulus for different. The Wikipedia page is pretty nice. Different materials. It gives it in different units. So gigapascals, pascals are newtons per meter squared. So they're useful for us. We'll talk about more on that. I don't know. I would imagine it's probably pretty much the same, Sammy, but I'm not sure. I'm not sure. Biologists might know if there's a big difference between the pliability of bones in different types of animals. Anyway, so remember that G is, what is that, 10 to the 9th? Yeah, someone sat down and figured out how much pressure it takes to break a bone or to pull a bone apart. Yeah. Science, you might think it's useless, but you might end up with a case where you need to know that for some reason. These are 10 to the 9th. So you can see rubber gives pretty easily. And then you have different metals and different, graphene has a really high Young's modulus. Copper is decent. I think some of these are steel. Tungsten, 400. Wrought iron is about 210. So 2 times 10 to the 11th newtons per meter squared. So tooth enamel, it's actually kind of neat to look at this stuff. But as far as we're concerned, these are plug and chug. I'll show you how we use them soon, but they're really plug and chug questions. If you're an engineer, you need to know this, because imagine you want to know how much pressure you can put on a concrete pillar before a building collapses. Like how much weight above you want to put on something before it actually smashes down. What is the volume change of a cubic meter of water? So the pressure at the bottom of, let's say, well, we'll get into this, but let's say that there's a pressure of 8 atmospheres, which is, an atmosphere is, I'm trying to see if how I want change this into pascals. So let's just say that 8 atmospheres is about 800,000 newtons per meter. Okay. So at a pressure of 8 atmospheres, it's about 1.01 times 10 to the 5th newtons per meter squared is 1 atmosphere. We'll talk about that when we do fluids. So at a pressure, what is the change? And if you think that's a big change, that's not very far down. We'll talk about that when we talk about fluids, but this could be not, I think maybe a mile down in the ocean might be 8 atmospheres, and it might not even be that far. It might be a lot less than that. So we know that force over area, which is pressure, is equal to beta delta V over V. Okay, and so modulus for water is 2.2 times 10 to the 9th. So if beta is 2.2 times 10 to the 9th, and this is newtons per meter squared, then if we want to know the fractional change, that would be F over A times V over B. A cubic meter has a volume of 1 times m to the third. So delta V would be, F over A is our pressure, 800,000. Our volume is 1 meter cubed, and our beta is 2.2 times 10 to the 9th. Now this is 8 times 10 to the 5th. So this would be 800,000 divided by 2.2 divided by 10 raised to the 9th is 3.6 times 10 to the minus 4 meter cubed. That is very small. So even at 8 atmospheres, water doesn't get that compressed. When we do fluids, we're going to talk about the incompressibility of water. Water doesn't compress at all, really. It's not as good as steel stretching, but 3.6 times 10 to the minus 4 meters cubed is a very, very tiny volume of water.
Excuse me.
Yes.
I have a question about the units. For the pressure, force over A is Newton per meters.
Squared.
For pressure, you write down Newton per meters.
It's meters squared.
Well,
Sorry, area is meters squared. I don't know where I wrote. Where did I write that? If I did write that somewhere, I'm sorry that I wrote that.
you wrote that.
I don't know where I wrote that. But yeah, pressure is Newton per
Yeah, it is a slide Newton per meters.
Yeah, it's newtons per meter squared. Oh, yeah, I wrote it here, sorry. Yeah. It's pressure is force over area. Area is meters squared. Delta B would have meters cubed. Volume would have meters cubed. And all of these, Young's modulus, bulk modulus, they all have units of pressure. So that the pressure divided by the modulus will give you a whole number, just like delta V over V or delta L over L or delta X over L, I mean. So that's all with this stuff. What we've learned from this is that in equilibrium, the sum of the forces in X and Y and Z all have to equal 0. The sum of the torques have to equal 0, all axes. And then the other thing we learned was F over A is equal to Young's modulus for a fractional length change. F over A is equal to this shear for a deflection, and pressure is equal to fractional volume change times that, the bulk modulus. That's all there is in this chapter. I want to go now to some problems using those things that I gave you. I gave you a couple of these I didn't give you. Oh, where are you? And this is the second PowerPoint on problems. Some of these are pretty hard. And a couple of these are your homework. So here, a scaffold. If you don't know what a scaffold is, a scaffold, let me do this. Come on, open. I don't know why that thing didn't open. All right. Why isn't this thing opening? Okay. Oh, because I'm probably done. Anyway, scaffold. If you don't know what a scaffold is, all a scaffold is it's just a straight rod, basically, if you think about it. It's those things that like painters stand on. So we're saying that the scaffold has a mass of 47. So I'm going to call this MS, is 47 kilograms. And its length is 5.4 meters. It's supported in a horizontal position by a vertical cable at each end. So I'm going to call this A and B. And a window washer stands at a point 1.2 meters from one end. So if I go this way 1.2 meters, I have a guy who's standing like painting, okay, or washing windows. I want to know what is the tension in A and B with him there. So we can draw this bar as having a tension A and a tension B. And we can draw the weight of the scaffold. Weight of the scaffold is mg. And then we have the guy, and his weight is, I'm going to put it MWG. And MW was 63, and we know that he's 1.2. Okay, so some of the forces are TA minus the mass of the window washer times G minus the mass of the scaffold times G plus TB. I can't solve that one because I don't know TA or TB, but I can do torques and eliminate either TA or TB. So I can either do a torque here or a torque there. Or I can either find the sum of the torques about here or about there to eliminate A or B. I'm going to start with the right side. So this was 1.2 meters, mass of the window washer. This thing is 5.4 meters long. So where is the center? L center is at 2.7 meters. So at 2.7 meters, that's where the center of mass of the scaffold is. And then finally, at 5.4 meters, I have tension B. And this thing rotates that way, I'm assuming. So let's look at each of these tensions. At 1.2 meters, I have MWG. This is my R, by the way, for the washer. At 2.7 meters, I have R for the scaffold, M as scaffold G. And at 5.4 meters, I have tension B. So this is RB. This one turns positive if I'm assuming this is positive. This is negative, this is negative. So some of my torques around axis at where tension A is 5.4 TB minus 1.2 M minus 2.7 MSG. I can solve this since it's equal to 0 for TB. I'll do that up here. TB is equal to 1.2 M washer G plus 2.7 mass scaffold G divided by the 5.4. All I did was I moved these two terms over, divided everything by 5.4. Now, going back here, 47 and 63. Mass of the washer was 63 kilograms, mass of the snow was 47. Plugging those in with G being 10, I get 1.2 times 63 times 10 plus 2.7 times 47 times 10, divide that by 5.4, and I get 375. Once I have this, I can do one of two things. I can go back and I can plug in 375 and plug in mass of the scaffold was 47, so minus 470. Mass of the washer was 63, so minus 630. And 0 is TA. So that's 1100 minus 375 is 725. So TA is equal to 630 plus 470 minus 375, which is 725 newtons. So 725 and what was it, 375? And there you go. That's it for equilibrium. You just have to figure out how far away they are from your axis. It's not too bad. The next problem is a little tougher than that. Here we have two masses, A and B, and they're hanging from two tensions with different angles. And we're going to have to find these angles. And this problem looks absolutely horrifying. Absolutely horrifying. Except when you start to realize, okay, instead of looking at this, you can actually break these up into two different, this is T1X, this is T1Y, this is T3Y and T3X, and, well, I don't want to do that, actually. I have T2 and T2, and I have MBG and MAG. And each of those free body diagrams, this is the free body diagram at this point, and this is the free body diagram at that point. The acceleration in X and Y are 0. I do need to remember to do what these are. So this along Y is T1 cos of phi. This one is T3 cos of theta. This one is T3 sine theta, and this one is T1 sine theta. Okay, so I have the forces in the X, MAX, are equal to T2 minus T1 sine theta is 0, or T2 is T1 sine theta. And MAY, of course, this is for this one, is T1 cos phi minus MAG is 0, or T1 cos phi is MAG. Now, we're told the weights. So a weight is MAG is the weight of A. That is 38 newtons. And weight of B is 48 newtons. And we're told that phi is 39. So at this point, we want to find T2 before we even worry about B. We want to find T2. Now, T2 divided by sine of, oh, and I'm sorry, these should be phis. Is T1, and T1 is MAG divided by cos phi. So that would be MAG is 38. I know that phi is 39, so over cos of 39. So 38 divided by cos of 39 is 48.9. Let's just call it 49 newtons. So T1 is 49 newtons. What just happened? And from this, I know that T2 is T1 sine of this angle, which is 49 sine of 39. So T2 is 49 times sine of 39, which is about 30.8. They're not related at all, Sammy. They don't need to be related at all. There's no relationship between them. they're kind of the same, but watch what's going to happen now. So now we know that T1 and we know T2. And we don't know theta, but we know that MBG is, what is it, 48 newtons? And we got that T1 was 49 newtons and T2 was 30.8 newtons. So doing the same thing from these, I get that T2 minus, so MBAX is 0 is T2 minus T3 sine theta, and MBAY, which is 0, is T3 cos theta minus MBG. So T3 is equal to T2 divided by sine of theta, but I don't know what theta is. And so let me actually go back and do that a slightly different way. So if T2 is equal to T3 sine theta, and I don't know what T3 is, and I don't know what theta is, T3 is equal to T3 cos theta is equal to MBG. I don't know what, again, these two things are. So I can do something actually kind of fun here. Since MBG is equal to T3 cos theta and T2 is equal to T3 sine theta, I can divide these two equations. This is 30.8 divided by 48. And that's equal to the T3 cancel, and I get tan theta. So theta is equal to arctan of 30.8 over 48, which is arctan of 30.8 divided by 48 is 32.7 degrees. And now that I know that, since I know T2, I have T3 is T2 divided by sine theta. So 30.8 divided by sine of 32.7. And I get 57 newtons. So now I need to go back and look at something really fast, and that is, there should be nothing here and nothing here. Of course they're not, because there's a tension 2 and a tension 2. They point in equal and opposite directions. So it's not moving left or right. That also means that T1 sine of phi had better equal T3 cos of theta. So I could have used that as well, just setting those equal to each other. Since T2 cancels, here I could have done MAG plus MBG had better equal T1 cos, T3 cos, right?
And T3 sine theta?
What's that?
It shouldn't be T3 sine theta instead of cos?
Where? Oh yeah, it should be sine. You're right. I was just writing fast. You're correct. And the ones that are up are T3 cos and T1 cos. So yeah, so this problem isn't even about torques. It's just the fact that you know the forces are 0, that you can actually manipulate stuff around. It's a really fun problem. Try and do it again on your own. This is actually one of our homework problems. I don't know if I included the picture. I think I did. Maybe I didn't. Anyway, this is one of our homework problems where basically they give you a scaffold and a bunch of paint cans, right? You know that the scaffold has that and tension A and tension B, or tension left and tension right. when you do this, it tells you that somewhere in here, you're going to treat it as if all of these paint cans are just a simple mass. At some point, you don't know where. The total mass of the paint cans, you're told M of the paint is 74.6 kilograms. And you're told that TA is 747. So now, some of the forces on this would be, because this is going to have a weight, would be TA plus TB minus mass of the paint minus mass of the scaffold is equal to 0. The torques, now, being that you don't know tension B, it makes the most sense to put your axis of rotation at TB. When you do that, you're going to get at half the length. So I'm going to write it as L to the half is mass of the scaffold. Unknown is the distance to the force, the weight of the paint cans. And then total L is tension A. Once you get good at these, you'll know that you can write them pretty fast. Assuming this is positive alpha, I get L to the half mass of the scaffold G plus unknown, which I'm just going to call R, mass of the paint G minus LTA is equal to 0. What you're going to find here is that you're solving for R, right? So R, mass of the paint cans times G, is equal to LTA minus L to the half mass of scaffold G. Now, L is 2.02, so this is 2.02 times tension A was 747 minus 1/2. What is the mass of the scaffold? 48.4 times 10, okay? That's going to give us 747 minus 0.5 times 48.4 times 10. On your homework, use 9.8. And then I'm going to multiply this whole thing times 2.02. So I get 1029.87 is R mass of paint G, but R is going to be 187 divided by MPG. MP is 74.6, so divide that by 10 times 9.8 times 74.6, and I get 1.4 meters from this side. This is 1.4. How far is it from this side? Well, it's 2.02, so 0.62. Just make sure that you understand it's from TB is where we found it. All right, so 2 more that I want, well, 3 more that I want to do. I don't know why I doubled these up, but I did. So just ignore that. So here, this problem is a homework problem. We have this guy, and we're given that A is 0.985, and we're given that D is 0.94, and L is 1.90. And we don't know his mass. We're assuming that this is frictionless, and we're assuming that there is friction here with mu. What are the forces? Here we have N in the X, we have mu, and Y, we have NY. Just like before, just like the ladder problem. It's the ladder problem. Somewhere here, we have his weight, mg.
Excuse me, it shouldn't be mu and x in the horizontal?
No. It's mu ny.
Why?
Because it's the normal force being applied at the point where his feet are, which is ny. So here, his normal force, ny.
Oh, I get it. I get it. Thank you.
So this is mu ny. Okay. So now if we just do the sum of the forces in x and the sum of the forces in y, and they're both 0, because we assume nothing's happening, right? We get nx minus mu ny, and we get ny minus mg. And that's it, right? So we want to know what mu is. So mu is nx over ny from this equation right here. Just move that over and divide by ny. But ny is equal to mg. So we have nx over mg. But how are we going to find nx? Well, obviously we're going to need to do a torque. So if we take this to be the axis of rotation, we can ignore ny and the force of static friction. And so we get at D and at L, right? So at D, we have his weight down. Oh wait, I take that back. I take that back. I take that back. We don't know his mass, do we? Yeah, so sorry. So I don't, do I want to do that? No, I don't want to do that. So not knowing his mass, I'm going to need to take the torque about here. But this seems wrong to me. Seems like something's missing here. Maybe I'm wrong. Why do I not? Oh, no. I'm dumb. I'm beyond dumb. Sorry, guys. I can take it from here. Because, so the torques will be at D, mg, and at N, or at L, nx. So I need to figure out what these two torques are. So if I go D to mg, I want D perpendicular. So D perpendicular to whatever this angle is, right, is D cos theta. And this torque, I'm going to assume that way is positive. So I have D perpendicular and I have mg, or if you want it drawn more correctly, mg. So this torque is D cos theta mg. Now, this one that goes all the way up to L is nx. And so I want L perpendicular to nx, right? Which is L sine of theta. L sine theta. So this torque, nx, L sine theta, this is negative L sine theta nx. Some of the torques about that axis are 0. So I get D cos theta mg minus L sine theta nx. I want to solve this for nx. So nx is equal to D cos theta mg divided by L sine theta, right? I should note that tan SOHCAHTOA is opposite y over x. Don't need that, sorry. I want to come back to something, so I want some more room. So if nx is d over L mg cos over sine, d over L mg cos over sine. Okay. And going all the way back here, I want mu, which I said was nx over mg. So mu is d over L mg over mg cos theta over sine theta. Now cos theta over sine theta is 1 over tan theta. What is theta? In this picture, you're given A and you're given, you're assumed we're assuming that we're given L. It's weirdly drawn, but A and L, right? So from SOHCAHTOA, if I know adjacent and I know hypotenuse, that's cosine. So cos theta is adjacent over hypotenuse, or theta is arc cos of A over L, okay? So you can find theta this way. And this is d over L cotan, if you want to call it that, or you can call it 1 over tan theta. I'm not going to put these numbers in, but they were all given to us. We find theta from A over L, d over L. The main point here is that you're going to have to use the torques to find nx, which is kind of difficult, but okay. This one I'm not going to do because it's going to take a while. We can do it Thursday. But there is a stretched length in here. So if you can figure this out, great. If you can't, wait till Thursday. The last thing I wanted to talk about before we're done is this problem is pretty nice, but it's also kind of a pain. So I want to talk about this problem with you guys really fast. Because it uses stuff we've already learned and Young's modulus. So in this problem, they're saying that there's this floor, and in between these two floors, there are a bunch of springs. And a bunch of people, it says 20 people with a combined mass of 1,200 kilograms. So if we place 1,200 kilograms of mass evenly over the floor is what we're going to be talking about. So the floor has an area. The area of the floor, cross-sectional area, will be 100 meters squared. It's got two stiff plates with coiled springs between them and an equilibrium separation. So these are initially at 0.05 meters separation. The spring constant for each spring is K is 1,000 newtons per meter and 20 people. So first, what is Young's modulus for this floor? Okay, so Young's modulus for this floor, we have F over A is equal to E delta L over L. Now, if we want to find the spring constant though, remember that the force for a spring is minus Kx. We're going to assume here that essentially X is equal to delta L, which I guess, so here K is equal to F over delta L. Now, remember that F over A was Young's modulus delta L over L. I guess I just wrote that there. So F over delta L is equal to EA over L. And here, we're going to assume that Young's modulus, they gave it to us, I thought, or am I wrong? Boom, 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 boom. Did they give us Young's modulus? Am I crazy? Oh no, they gave us K. but we need to find Young's modulus. So sorry, K is equal to E A over L, and we need to find E. So E is equal to KL over A. In this case, K for each spring is 1,000, but we have 100 of them. So we need to multiply by 100, so K total, which would be equal to times 100, which would be equal to 1 times 10 to the 5th newtons per meter. L is how far apart they are. So this would be 0.05 and dividing the whole thing by the area of 100. So that gets rid of, it's 1,000 times 1,000 times 5, which is 50. But I'm missing a number. What went wrong there? 100 times 1,000. Yeah. 1,000 times 0.05. Or do they have it wrong? Oh, they have it wrong. They actually have this wrong. Their K. Why is their K wrong? Oh, because they say 100, but it's actually, oh, there's 100 evenly spaced identical springs per square meter. So sorry, I'm dumb. So this is not 100, it's 100 times 100. So 1 times 10 to the 4th. So there's 100 springs per square meter. So times 100 square meters gives us 1 times 10 to the 4th, but each one has a K constant of 1 times 10 to the 3rd. So this is 10 to the 7th times 0.05 divided by 100, which is 0.05 times 0.05 times 10 to the 4th, which is 500. So Young's modulus is 500 newtons per meter squared. To find out how much it is compressed, right? So we say, okay, delta L is how much it compressed. F over A is E, delta L over L, where E is 500 per meter squared. F is mg, but this was 1,200 kilograms times 9.8 if you want, newtons. We want delta L. We know that L is originally 0.05 and that A is 100 meters squared. So we want delta L. Delta L is FLA over E, which is 1,200 times 9.8 times 0.05 over 100 times 500. And this is going to be very small. 1,200 times 9.8 times 0.05 divided by 100 times 500 is 0.012 meters, 1.2 centimeters. Hopefully that's the right answer. Why are they getting millimeters? What did I do wrong? I don't know. Oh, because this is 5,000. So yeah, since I've got that wrong, somewhere I've got a 10 off. The final thing though, the reason why I wanted to bring this up is this problem. Question C says how much elastic energy is stored in the floor. So let's think about this. Before the people step on this, it does have some H, where H is equal to 0.05. And then after it's been compressed by this force, H is 0.05 minus 0.0012 or whatever that was, right? But the spring energy, X is equal to 0 when this is still 0.05. And X is now compressed. It's this, delta X is 0.0012 meters, okay? So you could think of it this way. The energy before anyone gets on it is kx squared over 2 plus mgh, and the energy after is k x final square root 2 minus or plus mgh final. But we're only asking about the change in kinetic energy, or I mean the change in spring energy. Now, you can do this one of two ways. You can assume that X is 0 and it compressed to X is 0.0012, let's call it. Or you can go from X is 0.05 to X is 0.05 minus 0.012. Okay. Either way, it doesn't matter because the change in potential energy of the spring is going to be, and it's the negative, kx normal and final. So this is initial squared over 2 minus kx final squared over 2. And since it's the change in the negative signs don't matter, doing the 0, initial and final, this becomes negative and negative. So the amount of potential energy stored in the spring becomes k x final squared over 2, which is, what was this, 5,000 times 0.0012 squared over 2. Or using these, you would get k to the half times 0.05 squared minus 0.0038 squared. So that is 0.002. Which one of those is going to yeah, 0.05 times 0.05 minus 0.00. Sorry, this is not 0038, it's 0.038. Actually, that should be a 0. So 0.00, 0.04, what, 8 squared. So 0.05 times 0.488 times 0.04. This is 1.1856 times 10 to the minus 4. 0.0012 times 0.0012 is 1.44. So which one's correct? Why is that going in the wrong number? My brain is checking out right now. Let me make sure this is correct. So the changing elastic energy should be kx final squared over 2 minus kx initial squared over 2. That's how much energy is stored. So if we say that this is 0 and this is 0.0012, we should get the same. Oh, no, that's right. We have to consider this to be the equilibrium point where this is 0. So our final answer is, this is initial, is k, which is 5,000 divided by 2 times 0.0012 squared. You cannot, do not assume this was 0.05 because it's not. That x initial was that. That would be if it had been stretched from equilibrium. you have to measure 0 to be equilibrium from your spring. Sorry that I forgot to tell you that. So this is 2,500 times 0.0012 times 0.0012, and that's about 0.0036 joules. In this problem, they're saying 1/2 delta L, where their delta L is, oh, and I forgot their K is 10 to the 7th. I had it wrong. So 10 to the 7th divided by 2, so 10 to the 7th times 0.5 times 0.00118 times 0.00118 does give me 6.9 joules. Anyway, why not mg delta L? Now, this is a good problem to think about. So they're asking how much energy, what is the change in the spring potential energy? And we assumed that the energy was 0, and then we applied some force and it went down some delta X. So there should also be a delta potential energy of gravity, which would be mg h final minus mg h initial. And this would be kx final squared over 2 minus kx initial squared over 2. Now, why are the two things not equal? Why do we assume that the two things aren't equal? Why should the energy here equal the energy there? So the problem is we're adding mass, and so things aren't conserved. And therefore, there's no reason for the energy at the top, the potential energy of the spring would be 0. So we'd have kx initial squared over 2 plus mgh is equal to kx final squared over 2 plus mgh final. So h initial, let's say, was 0, and h final was negative 0.00118, I guess is what they're saying. Okay, and coincidentally, x final is also this. Therefore, this is 0, this is 0. This is kx final squared over 2 is equal to negative mgh final. But that's not true. That can't be true. That can only be true if there's no outside force. However, we added mass to this problem. So we actually had to do something. If we compute this, this would be 1,200, just this term, 1,200 times 9.8 times 0.00118. 1,200 times 9.8 times 0.018 is 13.9 joules, which is about double. The energy was not conserved, right? The potential energy of gravity that changed was, some of that was lost to heat or God knows what else. I don't know. But the change in potential energy of gravity does not equal the change in potential energy of the spring. It's actually double. And that's, like I said, due to a lot of things. Yeah, it's, I don't know. It's not a conserved system. Anyway, so on Thursday, we'll have a quiz about torque and rotation. So it'll probably be find the torques and tell me what the rotation is. It shouldn't be too hard, and we'll have a lab. In the meantime, check out your practice exams and your homework, and we'll start doing reviews on Thursday as well as doing a quick lab. That'll hopefully help you use the IOLab to prove to yourself where the tensions are. In the meantime, I have one thing for you to think about. Everything you just learned, I want you to figure something out. So I said that when you have the sum of the torques sum of the torques have to equal 0 if it's in static equilibrium, meaning it's not rotating. I'm holding this pen from one side. So if I'm holding this up with my hand, let me redraw that. So I'm holding this up in my hand, right? How come it's not rotating? Now, what I told you was, if you do think of this as having a weight down the pen and having some maybe force from my hand at half the pen's length, right? Well, if I put the axis of rotation here, this thing should rotate. So before Thursday, I just want you to think about that and tell me why this pen is not rotating. What am I missing? It can't just be the force of my fingers up and the weight of this down. I'm missing a force somewhere, and I don't know what it is. It's an issue. Now, this might be a trap, and it might be a problem where it doesn't work because your hand does all sorts of weird things. But if someone can try and figure out the answer to how this thing can be in equilibrium, not rotating, by Thursday, let me know. Other than that, I'll talk to you guys soon. Have a good couple days. See you.